So now we're starting chapter 13, talking about multiple regression. So we're going to try to cover sections 1 through 7, and section 8, regression diagnostics, is very similar to what we talked about in chapter 12. So I won't rehash those issues. And then 13.9, logistic regression. This is very similar to this section we skipped in chapter 12. And that's a case when the dependent variable is binary, when you have a 0, 1 dependent variable. So we're going to pick up that topic towards the end of the semester. So going from simple to multiple regression. Multiple regression is just an extension, but it's when we include more than one independent variable. So simple regression is pretty powerful, but there's some limitations. It's very simple. If there are some omitted variables in the statistical model, then the estimate of the slope coefficient could be biased, and there could be a lack of fit, meaning that we have not, in a simple regression, we have not explained much of the variation in y from our sole x variable, our independent variable. So this is just an illustration of what a multiple regression is. We have a dependent variable, say a home price, and instead of just one independent variable like square footage, you might also have location of the house and the number of bathrooms, and you could have an x4, x5, you could have many more independent variables in your multiple regression analysis. Okay, another way of thinking about this is imagine that you've got a simple regression model with one predictor. So you could plot those with a scatter plot and fit a line and easily visualize what's going on between the two variables. But with two predictors, you'd have to think about this in terms of a three-dimensional diagram. So here in this box, we've got the height of the box is the dependent variable, the y, and along the sides of the box, we've got variable x1 and x2, and these dots are floating inside this box, and then this plane is fit to those dots in some way. Okay, so multiple regression can get much more complicated. In terms of the math, multiple regression does not seem that much more complicated. All we do is string out additional variables and their coefficients in a linear model. Okay, so in this model we've got k predictors. K is the number of independent variables or predictors that are in the model. Okay, we've got an error term in the theoretical model, and then when we fit the regression line, when we estimate these coefficients, we'll call those lowercase v's, and y hat is the predicted y value, and we lose the error term. So here's an example. So this is with the same data that we have used in chapter 12, where we have home price, and I have changed the dependent variable. I divided each home price by $1,000. So we're measuring housing prices in thousands of dollars. And here's my multiple regression coefficients from the Microsoft Excel output. And if you take those coefficients and multiply them by their variable, you can express this as an equation, a linear model. So the price is equal to minus 108, and that's the number on the intercept, plus the first variable, square feet, which can be found in the second row of this table. So 0.0953 is the coefficient on square feet. And then lot size comes into the model with a negative sign. So we subtract lot size from the price of the home and give it a weight, this coefficient estimate of 3.996. And then the number of bathrooms is the last variable here, and it comes in with a positive sign, and the number is 82.897. Okay, and so since this price is measured in thousands, the square foot variable, we would interpret that as for each additional square foot of the house, the housing price increases by, we'd move this decimal to the right, 1, 2, 3 places. The housing price would increase by $95. Okay, I'm not going to worry with lot size right now because the t statistic is less than, or is not at a level that would make us think that lot size is very important. But bathrooms does have a strong t statistic, and so we would interpret this as each additional bathroom increases the price of the home by $83,000. Okay, so imagine you get a data set and you've got a lot of variables in there and you're trying to explain one of them with statistics. So there's at least 4 things that you need to think about in terms of choosing the regressors for the model. So logic, fit, parsimony, and stability. We'll go through each of these one by one. So first, logic. This means, the question is there a theoretical reason to expect a causal relationship between the predictors and the response variable? Okay, so a causal relationship means that the variables on the right-hand side of the model, meaning to the right of the equal sign, whether these variables can be used to predict y. Okay, so things like square foot of the house, you would expect that to have a positive effect on housing price. X2 might be if the house is located near a hazardous waste facility, so or near a landfill, or in a floodplain. Okay, in that case, you'd expect the effect of location to be negative to make the house sell for a lower price. And then X3 could be another variable, and we think it might matter, but we're not sure in which direction. Okay, it might be school district, or it might be a variable that correlates to a certain town. And so even though we might not expect that X3 has a causal relationship on Y, okay, it might be the case that we want to try to, we think it might matter, and so we'd include it just to see what happens, and that would be considered a control variable. Okay, so logic is important. The last thing we want to do is use every variable in our data set to predict y just to see what happens. Okay, and that's known as the everything but the kitchen sink model, and that's a no-no when you're doing regression analysis. So the second factor is empirical fit, and we've covered these topics before. That's the F statistic, the R squared, and then another one that we'll introduce in chapter 13 is the adjusted R squared. So the question is, does the overall regression model show a significant relationship between the predictors and the response variable? Okay, so in general, the higher or more, we want to choose regression models that are statistically significant in terms of the F statistic and that have a higher R squared. This adjusted R squared is what we're going to use to adjust the R squared for the number of predictors in the model. Okay, and then choosing a regression model by fit is a tricky one because it's not always the case that the model with the best fit or the highest R squared is preferred. Okay, sometimes you might prefer a model with a lower R squared. Okay, it might give you better predictions than a model with a higher R squared. A model with a higher squared might have some problems that lead to bias coefficients and poor predictions. Okay, so unlike simple regression, where you can estimate a regression model and just worry about a few things, the things we covered in Chapter 12, multi-regression gives us more things to worry about in terms of the number of regressors, if those regressors are correlated with each other. And so this is a situation where more than one model typically needs to be estimated to figure out which one's the best. And then sometimes there is not a single best model. Sometimes the best strategy is to present several models and discuss the differences and the similarities and conduct the secondary analysis of predictions and forecasting with more than one model. So the bad news is sometimes there's no easy answers when you're doing multiple regression. Okay, and parsimony is important. This means simplicity. Okay, so just like I said before, everything but the kitchen sink model might not be the best approach. So you want to make sure, you want to ask yourself, does each predictor contribute significantly to the explanation? So we're going to care about overall model fit, and then the ability or the statistical significance of each individual regressor, each individual predictor. And then are some predictors just not worth the trouble? I mean, do some predictors just cause confusion when we're trying to understand some sort of process? Okay, and so here's a cartoon from clubstreetpost.com, and if you hover over that, there's the website. So this is Occam's razor. Occam's razor says, when faced with two equally good hypotheses, always choose a simpler one. So here's a fellow thinking about two situations where, in the one on the right, A affects B. So that's the simplest. And on the left, he's thinking that maybe A goes through some process, it leads to another process, and then finally it affects B. So in our context, if the process on the right is has an R squared that's pretty much the same as the process on the left, you would choose the model on the right, or the process on the right. Okay, and then the last choice criteria for choosing regressors, the number of regressors and which ones, is coefficient stability. So the question here is, are the predictors, all those variables that you might use on the right-hand side of your model, are they related to one another strongly, and so strongly that the regression estimates become erratic or unstable? And this is a question we'll get to at the end of this chapter, and that's the topic of multi-collinearity.